Good morning, everyone. I am Ramarao. I am Geological Surveyor. My talk is about the gravity anomalies over the Indian Cratons and their broad geological implications, whatever we are going to get out of this analysis. Now, cratons are the stable part of the continent. They are generally believed to be characterized with major gravity loads. So, I have studied in detail about all the Indian Cratons. Next one, please. No, I started at in the global level. The first one shows the major geological provinces of the world. And the second one is the Google gravity image of the world in 2012 International Association of Geophysics Population. And I wanted to understand what is the major response over the different shield areas. Of the 12 shield areas, I found 6 are gravity lows and 4 of them are moderate gravity highs and 2 of them are definitely gravity highs like the South Western Africa and the Guyana shield areas are gravity highs. In the beginning part of my study, this I extended to the Indian context. The next one is the left one is the gravity image of India, and the right one is the tectonic difference, major tectonic difference of India. And you can see India can be divided into 3 zones. The southern India is populated with major gravity lows, and the central India you have got number of gravity highs, and in the Himalayan region is again major gravity lows. Okay. Now, in the Indian context, you see that the southern India is mostly characterized with gravity lows, which is having 2 major cratons, that is the Dharwar Craton and the Basar Craton. And the Bundelkhand is central part of the Bundelkhand Craton, which is a mixture of both gravity lows and highs. And the Meghalaya part, which is a geological paradox, whether it is exactly a craton or a mobile bed. And the Singham is gravity high zone. And similarly, Rajasthan Craton in the western India, if you see, this part is populated with major gravity high zones. This is the starting point of my study of gravity anomalies of the Indian Craton. And what I did was, I have regraded the data craton wise, and I applied same parameters for processing the data. And I did both qualitative analysis to understand the nature of the crust beneath the cratons, and I also did some quantitative analysis of frequency analysis to know the major depth interfaces, where are they exactly occurring. Okay, this is the study what I have conducted. Yeah, the first one is the Dharwar Craton. This is the most important geological domain in the southern Indian shield area, and it has got a definite boundary with the Chartacetic region of southern granulate terrain in the south, and in the east it has got Eastern Ghat mobile bed, and it is periphery with the major igneous province of India, that is the Deccan volcanic province. Now I found 3 kinds of gravity highs in a regional level in the Dharwar Craton. We have got a 3-dimensional huge gravity highs, which probably reflect the, you can see major gravity highs. You can see major gravity highs, which are 3-dimensional occupying large areas. Probably they reflect the magma chamber in the upper part of the crust. And you also have 2-dimensional gravity highs, which probably reflect the upper of the lower crust, and the high frequency gravity anomalies probably reflecting the surfacial features. So what I am trying to say is, I have attributed the first interface, whatever I have done in frequency analysis, to the extent of the intrusives into the craton. And the second interface I assume is the boundary between the upper crust and the lower crust. And the third interface I attributed to the Moho bond. Okay. Now, I have also drawn for every degree from west coast to east coast the gravity profiles, and I found that the dashed lines show a major upward region, which is reflected with a gravity high zone, dividing the Dharwar region into the western part and eastern part, and this sufficient thick region I attributed to the central craton part of it, which have characters of both western Dharwar and the eastern Dharwar. The gravity hump I have modeled for the upper of the the lower crust and the at mantle level also, at the mohole level also, that remodeled this part of the gravity anomaly. And I see this sudden jump in the gravity profile, which I have seen for about 5 degrees extent. I attribute that this is due to the upwarp of the lower crust. And I found 3 interfaces for each craton. Next one, I also did the low pass filtering, applying the same parameters. You can see the high frequency anomalies, how they are persisting. To my great surprise, what I found is the gravity anomalies as we go deep into the southern granular terrain are now greatly different from the craton part of it. So I believe that whatever the geological differences what we see are limited to the upper part of the crust, and the nature of the crust or the thickness of the crust is more or less same for both the craton part and the granular terrain in the south. And number of this map also shows the extension of the Dharwar Craton into the igneous province, that is the Deccan Volcanic Province. The signals are very strong to say that Dharwar Craton does exist beneath the Deccan Volcanic Province. These kind of inferences I could make. And I also did the vertical gradient and the both x and y directions. I have calculated the gradients, and I did Euler 3D solutions. They gave me an idea about the nature of the attitude of the gravity anomalies, and also the light activity. You can clearly see in the east west. You can see the number of eastern features. These are the major dike activity in the eastern Dharwar Craton. And the depth solutions gave me an idea about the depth extent of the intrusive into the craton. The next important geological domain is the Basar Craton. It has got a definite boundaries of Godavari zone in the west and Maharajari zone in the northeastern part of it. And in the central part of the craton, there is a major gravity high zone. Probably this also can be divided into 2 parts, the western part and the eastern part. The eastern part is predominantly gravity loose, and the central part, only part of it is definitely granular belt is seen in this part of it. So this is a kind of inference I could draw in the Basar Craton. This is a very major geological domain. It has a large potential for mineralization also. I did the same set of filtering, and the gravity high, whatever I have found out in the central part, it persisted throughout even in the much deeper levels. So probably there is a definite case to say that when divide this craton into the western part and the eastern part, and the interfaces also are calculated. And the next one, similar analysis of the horizontal and vertical gradients, and the depth solutions give me an idea about the extent of each intrusive border. The next one is the Singham Craton in the northeast, in the eastern part of India. Now this is accepting the Singham granite body. This is predominantly populated with gravity highs, the Eastern Ghat mobile belt and the Satpura mobile belt, and the Singham cold belt, what you can see them. But this line probably, in my opinion, should be the actual Craton mobile belt contact, and this probably is an exception. In fact, the depth influences, whatever I got from this, also indicated that it has got the shallowest part of the crust in the Singham Craton. And I have also drawn the profile and did the same kind of exercise. Now, the third important craton is Aravalli Craton. Aravalli Craton, you can see in the western part, it is populated with the sandstone area, and the geology is very well exposed only in the eastern part of it. And you see a distinct nature of gravity anomalies in the western part and the eastern part. And probably the dispute that is separating the Marbar Craton and the Mewar region. And this area is mostly populated with a gravity high zone, which is quite unusual for any craton. The features, when I applied the low pass filter, same kind of low pass filters, it gave me a definite indication of this is a deep feature that is separating the western craton and the eastern craton. And the depth solutions and the gradients, whatever I have calculated. And the central part of the crater, if you see, which has got everything, because this is the first part of the craton under the Deccan volcanic province. This is the Bastar Craton, and the Central Indian tectonic zone separates the South Indian Shield area from the North Indian Shield area. This is the Bundelkhand Craton. This map clearly gave us an idea under the younger alluvium cover. You can see this should be the actual extent of the Bundelkhand Craton. Though from this part you can see this is all covered under. Anything north of this area is covered under alluvium area. These are the, and you can see number of gravity high zones, which probably suggests that the gneissic crust is very limited in this part of the craton, and probably you have more of a mafic crust in this part of the craton, whatever we want. And I also saw the extension. In fact, Central Indian tectonic zone really is a strong tectonic feature. It divides the South India and North India, and people believe that the South Indian features do not extend into the North India. But I can see that the Godavari zones, the alignment of these anomalies into this craton, but probably suggests that this must be the oldest feature. Similarly, you can see the extension of Mahanadi, the alignment of northwest southeast features are quite unusual in this part of the country. They are predominantly east-west or northeast southwest. This is the major trend of it. And we also found that a major gravity high zone under the Deccan volcanic region, which is similar to the supracrustal plates all along the Central Indian tectonic zone, whatever we have got. This is the Betul and this is Mahakoshal. This is also Mahakoshal belt. Similar thing under the cover we found out. And I have also put all the earthquake data on this, and it suggests that the Central Indian tectonic zone is extending into the Arabian Sea, and not as probably shown when joining the Rajasthan Craton. This is the earlier geological map, which suggests that this tectonic zone is probably something like this. And the gravity anomalies together with the earthquake data suggests that probably the tectonic zone is extending like this in this direction.